One of the important property of material is its mechanical properties. So today I will be solving some of the problems related to mechanical properties. Along with that, I will also discuss some of the concepts behind it. Welcome to Materials Horizons. See you after the intro. Thank you. Let's start with the problem. First problem. A tensile stress is to be applied along the long axis. Long axis means longitudinal directions of a cylindrical brass rod that has a diameter of 10 mm. Determine the magnitude of load required to produce a 2.5 10 to the minus 3 mm change in the diameter if the deformation is entirely elastic. Poisson's ratio is given. So we need to have we have to determine the magnitude of the load required to produce this change in the diameter. So these kind of problems, it's better to sometimes draw the diagram, right? So initially it's like this, then it will be elongated. That means the diameter is reduced, right? So final diameter, suppose di, and the initial diameter is d naught. Then the initial length, and this is the final length or instant length. That's why I am putting it I. So the strain we have to calculate. Strain means the deformation. So deformation in the along the axis. So this is z axis, okay, and this is x axis. So this is longitudinal direction, okay, that would be Li minus L naught by initial length, or del L by L naught. Similarly, in the x direction, this is given by di minus d naught divided by d naught. So this is del d by d naught, okay. But see, this is smaller, and that's why is ultimately negative. One term would be always negative, right? One will be increasing, another will be decreasing at the expense of others, okay. So when the force F is applied here, suppose F is applied, then it is elongated in the z direction, so experiencing a reduction in the x direction. So the change in diameter is given here in the problem, that is minus, as it is reducing, I have told here, okay, 10 to the minus 3 millimeter, or in meter that will 10 to the minus 6, right? So I don't require that, because see what is Ex, you will know that del D by D naught, and this is actually minus 2.5 10 to the power minus 3, and D naught in mm is also 10. So ultimately minus 2.5 10 to the power minus 4, and it is unitless, okay. So Ex we have got. So now we want to know what is Ez. So only one parameter bridging them is the Poisson's ratio. Okay, so this is the transverse part by the longitudinal strain. Okay, so if I divide it, so it will be minus, one parameter was minus, it is written in minus, so ultimately minus into minus 2.5 10 to the power minus 4 divided by 0.34 Poisson's ratio. Okay, because it is given here. So we are getting 7.35 10 to the power minus 4. So this is Ez, right? So what is the applied stress then? By the way, here an interesting fact is Poisson's ratio is given. If the Poisson's ratio is not given, in that case obviously another parameter, shear modulus, would be given, right? So for that we will use the formula E by 2G minus 1 equal to nu. Then we can get the Poisson's ratio, E and G if we have. This is shear modulus, Young's modulus, elastic. So what is the applied stress? Applied stress is given by sigma is E into epsilon z. I forgot to put here the E of the brush is actually 97 10 to the power 3 MPa, 97 GPa, right? So sorry, I just forgot to put it here. MPa into Ez, it will be given, right? This will be given for brush. Okay, so ultimately we are getting 71.3 MPa. Okay, let me wipe it. Okay, now we have to get what is the force applied. We have already obtained the stress applied, now force applied. F is equal to sigma into A naught, because that will be the force applied to get this deformation on the initial area. So that's why I have put A naught, and that will be sigma into d naught by 2 diameter whole square into pi. Okay, and if I put all the values here, 10 to the power 6, plus 6, because that will be Newton per meter square, right? Into 10 into 10 to the power minus 3 meter multiplied by pi. So what we get finally, 5600. So this is the answer. So this is the force we have to apply to get this sort of deformation in diameter. Moving ahead to the next problem. Here, a steel alloy to be used for a spring application must have a modulus of resilience of at least 2.07 MPa. What must be its minimum yield strength? E for steel given 2.77 GPa. So first of all, here we encounter this term resilience, right? And secondly, what must be the minimum yield strength? Okay, so resilience is capacity of a material to absorb energy when it is deformed elastically. Okay, so according to this definition, modulus of resilience is given, suppose you are integration 0 to, this is the strain at yielding when the yield takes place. So what we get, half sigma y into epsilon y, stress at yield stress, and this is the strain at yielding. So unit is actually joule per meter cube, which is equivalent to Pascal. So this UR is so far sigma y into epsilon y. This can be little bit rearranged to write, so sigma y square by E. This is the equation. Okay. So now the rest part is very easy. So they are asking for the yield stress. So yield stress is actually 2 UR, it's coming from there, and just simply if I put the values, 2.07, that is in MPa, into 207 into 10 to the power 3, that is in MPa also. Okay, just simply putting the values, we will get 925 MPa. Yeah, that's our answer. Because there is a what must be the minimum yield strength. This is the yield strength. Okay. This stress is actually yield strength. So moving ahead to the next problem. What are they saying? A cylindrical specimen of a steel having original diameter. So original diameter is, so again here similar kind of image. Okay, so initial, so this is actually after elongation. Okay, so diameter is reducing. So they are saying this is the fracture strength, and the cross section diameter at fracture is 10.7 millimeter. So the diameter is decreasing. Then the first question they are asking, determine the ductility. Ductility is change of that elongations. In this case no elongation is given, so we will borrow the values from the change in diameter. So percentage ductility will be reduction in the area, right? So in that case AI minus A naught by A naught into 100. So AI is instant, I mean during the fracture, what is the area? So it will be obviously less, so it will be in minus. So we will reverse these two terms, okay, to get the positive value. So area means pi r square, so pi d square by 2, so other parameters will be cancelled out. So I am directly writing only the diameter square, right, and initial is 12.8 whole square. So what we are getting, it has a 30% of ductility. What is the next question? Next question, it's interesting. They are telling what is the true stress at fracture. They are giving already the fracture strength is this 460 MPa, but the true stress is something different. Okay, so for that I will little bit give you the theory. So true stress is actually defined as load at fracture by instantaneous area at fracture. So that is the true stress. Actually we don't take this instantaneous area, rather we just take simply the initial area, cross sectional area, which is basically defined as the engineering stress. Okay, and this is the true stress. For true stress sigma t, this is actually area by instantaneous force by instantaneous area, right? And the true strain is ln ln li, that instantaneous length by L naught. Okay. If no volume change occurs in the system, then obviously at the instantaneous condition, that is equal to at initial condition, right? So by little calculation we have F by A naught into L naught into Li, so this would be sigma to 1 plus epsilon. Similarly, this Et, by simple calculation we will get 1 plus epsilon, right? So true stress I can see always is higher, means this term is added. So if I plot the stress strain diagram, we see this is true and this is engineering. Okay, so engineering is reducing here, but true stress is always increasing because of this, because we are taking always the instantaneous area. Okay, so that was the concept of true stress. But in the real system, the load at which the fracture must be computed from the fracture strength. So here this F is actually final fracture stress at initial area. So what would be the load? 460 into 10 to the power 6, this one, Newton per meter square, okay, multiplied by what? That area, okay, A naught. Actually we don't have that A naught, right? Okay, so I have to calculate, sorry for that. What is the A naught here? A naught is pi into D naught by 2 whole square. This is A naught. So if I put in that place pi into 12.8 divided by 2 whole square, so what we get? 128.7 millimeter square. Okay, so we just simply put here and make it SI, dividing by 10 to the power 6. So we will get F equal to 59,200 Newton. Okay, so this is the this is the force, this is the force applied. So if we want to calculate the true stress, that would be this A by AF, that is the area at fracture, not initial area. So that would be 59,200 divided by the actual area. The actual area is AF. Still I have not calculated that. What is AF? Let me wipe it out, then calculate. So this AF is again pi 10.7 by 2 whole square, okay, in mm square, right? 89.9 mm square. So we will put it in SI divided by 10 to the power 6. So that would be 89.9 divided by 10 to the power 6. So that would be in SI meter square, then we will get 60. Similarly here also we will put in SI, remember it. So be cautious about the unit. So this sigma T is 660 MPa. Obviously this is quite higher than this 460. That is the true stress. So going to the next problem and the last problem obviously here for today. A sharp edge notch 120 micron deep is introduced in a thin magnesia plate. Magnesia means MgO. The plate is then loaded in tension normal to the plane of the notch. If the applied stress is 150 MPa, will the plate survive? Would you answer change if the notch were the same length but was as internal notch here instead of the edge notch? So first time A, it is edge notch, right? At the B, it is internal notch. So suppose the body is like this. This problem comes from the fracture of material, and basically this happens for brittle materials, right? So these are the stress applied, right? And this is the crack. This is the crack which is having length C. Okay. So to calculate whether the plate will survive, we need to know the stress intensity at the crack tip, right? And need to compare with the fracture toughness of this material that is given. We can see this is the fracture toughness of the material. So if it is higher than the fracture toughness, then obviously the material will fail, and vice versa. So let us do that. What is the stress intensity at the crack tip? Is given by sigma, that is the stress applied to pi into C. This C is actually effective crack length given by 150 into 3.14 120 10 to the power minus 6. Okay, so this would be 2.91 MPa meter to the power half, 2.91, and here magnesia has a 2.5, so obviously it is higher. So this H notch, because of which it cannot survive, this plate cannot survive, it will crack and it will break easily, right? So it won't survive. And the next, in the case of B, the crack is internal crack. I mean, then the body is like this and the crack is like this. So the crack length is again, this is the crack length. So in this case actually effective crack length will be half, because this is actually 2C. During calculations we do that. Okay, this is actually 2C. So we always take the half of this as a C. But the crack length is not changed here. So 120 micron is the crack length. So obviously we divide it by, so that is actually 2C. So C equal to 60 micron, or in other sense 60 into 10 to the power minus 6 meter. So what is the stress intensity in this case at the crack tip? Sigma root over pi C, same formula. We will put 150 into 3.14 into 60 into 10 to the power minus 6. So that will give rise 2.06 MPa meter half. Okay, so we see here this is 2.06, but the material has fracture toughness 2.5 MPa per meter half. So it meter half. So it means it has less stress intensity at the crack tip, so it will easily survive. So the material is safe in this case. So that's it for today. These are the problems we solved and this comes basically in the chapter of mechanical properties of materials. In future maybe I may add up some other problems also related to these mechanical properties. These are very important for materials property point of view. Thank you for watching it. Please don't forget to like, subscribe and share. See you in the next video. Bye bye.